Okay, welcome to the week 10 statistics webinar. So we're almost towards the end, see the light at the end of the tunnel, but there's still some more important stuff to do. And thanks for coming. And let me share my desktop and I'll talk about what the plan is today. Okay, so let me tell you the plan. What we're doing today, as always, I'll start out with any questions. If you have any questions, I'm always happy to answer. And then we're moving to regression analysis. So today is the regression analysis day. It's one topic. It's chapter 12, by the way. So we're towards the end. And it's not a small topic in terms of importance. It's a really important topic in terms of usefulness. It's just used all over the place. So in regression analysis, you have all kinds of different things that you can look at. What we're going to be looking at is for the regression analysis we do in this class, we're going to be looking at two quantitative variables. And we're going to say, well, if you know or want to find out how do you predict the second variable if you know the first variable's data, how can you do that? And that's what regression analysis is all about. It's all about this prediction idea. So one of the things you can do is you can draw a picture. If you have two values for each point, you can draw points in the XY plane and you can draw a scatter plot. Then you can do what most of you have heard of before, correlation. You've heard that word before. I'm going to guess that none of you really know what it is mathematically because it's very intense actually. And we're not going to get into the mathematics of correlation because it involves hardcore calculus and not doing it. But what I want you to understand is if you're given the correlation, which is a number, what does that tell you? So that's what we'll be looking at. And of course, we're going to be finding that number by letting the calculator do all the work for us. So that's going to be the plan. And then, so correlation, the letter we use is going to be R. And then if you square that number, you get what's called R squared. Hopefully that's not a big surprise. But it turns out that that has meaning also in itself. And the meaning of R squared we'll talk about. In fact, the meaning of R squared is the most difficult part of regression analysis for most people. So I'll get into that. And hopefully with an example or two, you'll see it. And I'm going to do this by example. I'm going to have a couple examples to look at, but they're all going to be related. And then we're going to get into, if you're given that scatter plot, you can maybe visualize a line that doesn't go through all the points because, 2 points makes a line, not 50 points. But maybe the points are somewhat on a line, but not really on a line. And the best fitting line to those points is called the regression line. And we're going to be looking at the equation of the regression line. So when you look at the equation of the regression line, and hopefully you know from beginning algebra, there are two important numbers when you're talking about a line. What are those two important numbers? What are the important numbers? The slope and the
intercept.
Yeah, the y-intercept. So the slope and the y-intercept are the two important numbers. Now, unfortunately, for most of you and me too, when I did this in, when I was in K-12 and I learned about lines, I learned how to graph a line, find the slope, find the intercept, but I didn't really get ideas of what the point was. Why do you care about the slope? Why do you care about the y-intercept in terms of the real world? But in this class, we're going to be talking about what does the slope tell you about the variables you're looking at, and how is that going to help you make decisions? And what does the y-intercept tell you? And can it help you make decisions? If so, what decisions might it help you make? And if not, why not? Okay, why will it not help you make decisions? So that's the idea. And nowadays, believe it or not, now they teach it. But I don't think any of you are quite young enough for it. Probably in middle school, you didn't learn those things. You just learned how to graph a line, or ninth grade, whenever you did it. Nowadays, actually, it is standard in the curriculum. If any of you are going to be teachers, you'll be teaching that. So we'll talk about the regression line, in particular the slope of the y-intercept. And then I want to emphasize, and this is pretty much for the entire class, is that you cannot use just about anything in statistics to talk about causation. You can only talk about relationships. You cannot talk about this causes that. So I'm going to talk about what to avoid and how to be careful about the way you react and talk about what the regression line tells you so that you don't make that causation mistake. And it's a very common mistake. I hear it all the time. It's the #1 math mistake people make in the real world is causation. And we're going to find out that's not something you can do from math. Causation comes from other subjects, not math. Okay, then we'll look at a hypothesis test for the correlation. And that is going to help us be able to say, yeah, we have evidence to show that there really is a correlation between the two things. Okay, versus we don't have evidence to show that. So we'll have a hypothesis test for, and this is one of those weird things. Most of you probably don't speak Greek and read Greek, but this is a Greek letter. What letter, what does it kind of look like in the English alphabet? Yeah, it looks like P, but it's not. It's not related to P. Again, don't get mad at me for this one. This is rho, and it's related to letter R, actually. Isn't that weird? So again, it's just one of those weird things about alphabets. So this is the Greek letter rho, which is the Greek letter for R, which is why we use R and rho for correlation, because that's the same letter, just in different languages. Okay, it's kind of a curly looking P, but it's actually it's a Greek letter for R, which is rho. So that is the plan today. I want to give you one little heads up. Always good to know. I always like to give you a reminder, and that is on the 20th, you have your project 2. Do not wait till the 19th to get it moving. Okay, the hope is that several days before the 20th, you've got a good full draft written so that you can send it to me. I'll look at it and give you some advice. That's the idea. Again, I know it's still 12 days from now before it's due, but I'd say, a week from now would be a good time to have a draft done. And that way I can look at it and you got plenty of time to take my suggestions and make them happen. So that's just a note about project 2. Also, this week, this is week 10, and 10 is an even number. Why is that important for this class? Yeah. Exams happen on the even number weeks. So you do have your week 10 exam. So make sure you, put enough time in your schedule. And you don't want to even touch the week 10 exam until you're done with the chapter 12 assignment, because that will help you on the week 10 exam thoughts. Okay. And just a reminder, I mentioned it on literally day 1 in the orientation. Around half the exam or so covers the newest 2 weeks of material since the last exam, and the other half is review, is the old material. So if you're wondering what the exam covers, that's how it always works. So that is the plan today. Let me ask, are there any questions about anything? Great time to ask. You can pop in the chat, you can talk, whatever you want to do. I'm always happy to answer questions. This is your chance to have real-time answers. See y'all jumping in. All right, well, if there aren't any questions, if you come up with questions, you can still ask in the middle of what, well, you know, when we're doing this stuff, but, and of course you can post on the Q&A board or the Project 2 discussion board, and I'll be happy to answer, but let you know that I'm here for you. And also Braulio has his office hours and he's here for you also. So there's plenty of chances to get questions answered, but I always like to make sure that there's a chance during these webinars too. Okay, so what I want to talk about is regression analysis. And again, regression analysis, what it looks at is two quantitative variables where you use one variable to predict the other variable. So it's different than, say, chapter 10, where we just wanted to test to see how far apart the variables were. That's actually not what we're doing in this one. This is about using a variable to predict another variable. Okay, very different. And in fact, in chapter 10, when you did a difference between them, what do you mean by predict? Okay, so if I tell you that I saw someone in elementary school and they were in 3rd grade, do you have a better idea about how tall they might be than if I didn't tell you what grade they were? If I just said I saw someone in school? Yeah, you have a better idea. Do you know exactly how tall they are? If I just say they're in 3rd grade? No. But you have a better idea. So if you're given the information from one of the variables, that helps you predict what the other variable's number is going to be. Okay, and that's what regression analysis is about, is it helps you predict based on the knowledge of one, what the other one is likely to be, using what's called a linear regression, is what we're doing in this class. And by the way, in advanced classes, there's more advanced than linear, but in this class, we just do linear. And also in advanced class, there's more advanced than just 2 variables, but in this class, we just do 2 variables. Just let you know that if you take a next stats class in upper division, you do a lot, you do more with this stuff. But we're gonna stick to linear regression, which is 2 variables and just a prediction of one based on the other using a line. So that's the idea. The variables do not have to be continuous. No, variables do not. In fact, the example I gave wasn't, right? What grade are you in? 3rd grade, that's not continuous. You're in 3rd grade, you're in 4th grade, you're not in 3.2 grade. That just doesn't make any sense. So they definitely, the variables do not have to be continuous, but they do have to be quantitative. Okay, that's necessary. Okay, you can't have like, you know, color of eye versus color of hair. Okay, then you'll be able to use one to predict, but not using linear regression. That won't work. So it's got to be quantitative. Okay, any other questions? Questions are great when you have them. All right, so I want to mention a few things, and I'm going to talk in general first, and then we'll do an example. So in general, we're going to have what's called the correlation. And you've probably all seen or heard the word correlation and had a somewhat light feel of it. And even after this class, you're not going to have a heavy feel of it. You're not going to understand, you know, the calculus of what's going on, but I'll give you the idea. So the idea is, first thing is the correlation is always a number between -1 and 1. Okay, and that's just part of the math. Just go with it. If you look at the scatter plot, and maybe I'll do an example just for fun. I'll just make up some numbers. So first thing, if you go to the calculator, we're almost at the end of class, so it should be easy to know where to find it. And that is regression analysis, 24. So next week's our last week, and that will be ANOVA, by the way. But we're in regression analysis. We've already done homogeneity. That was last week. So now we're here. And I created this calculator. There are 2 ways of coming up with your stuff. And I'm going to show the first way first, and I'll show the next way next. So let's do an example, and I'm going to do an example with y'all. And the rule in the class, by the way, is you don't have to be honest, but you have to give me something reasonable. And I do want data. Otherwise, we're going to have trouble finding anything. And we only have a sample size of 5. That's all we got here. So let's do something. And let's look at 2 variables where you think that one might help you predict the other, and they both have to be quantitative. And I'll open this up just in case you have some thoughts. Any curiosities? This is about each other. So you have to ask 2 survey questions about each other that are quantitative. Okay, temperature outside. How much will I eat? That's a good one, but the problem is I'm asking you right now, and you're all gonna, the temperature outside, unless you're not in Tahoe, that might be tough. How long you been in college and how old you are? Okay, sounds good. And again, that's a better one because everyone's gonna have different answers. Okay. All right. So, and by the way, as I mentioned, if you don't feel comfortable about the answer, you can lie. Don't say you're 195 years old because that's not reasonable. Okay. Don't say you're 0 years old either because you're not infants. So throw in your data. So the first variable will be how long you've been in college, and let's do by. What do you want to do by years, or let's do by quarters? Maybe quarters, because again, some of you this is your first year, and it's not even a whole year. So how many quarters have you been in college since you started till the end? Maybe I'll start, and I'll put in the chat box. Boy, this is going to be tough for me. Okay, actually, we'll look at one. I don't like to give names because there's privacy, and this is on YouTube, but I'll write down numbers. So we have 4, 22. So I'm going to type in 4 and 22. Plot points. And there we go. Okay, and then we have 13 and 30. So everyone has to do it. Probably that's including you too. And I'm going to do it too. I'm going to surprise you on both numbers probably. Okay, 16 and 29. Okay, so notice, by the way, we already have 3 points, and we have a scatter plot that's drawn. The points do not all lie in a line, which is typical. They usually don't, but it looks like they, might go up. Okay, then there's me. I'll put mine in too. This is going to take some math actually to calculate the thing. Let's see. Oh, we have another one? Oh yeah, we have one more. That's right. Sorry, 24 and 37. And then there's me, and that would be, sorry, it's going to take some arithmetic here. Let me just keep going just a minute. Okay, so like I said, I'm definitely an outlier. I've been in college for 111 quarters, and I'm 55. So let's plot, and there we go. Okay, so what we can do is we can look at this, and we can first take a look at this plot. This is called a scatter plot. And what that is you draw your axes for the 2 variables, and you plot the points. So you'll notice here's the point 111, 55, et cetera, et cetera. And there's all the points, and that's the scatter plot, are the points drawn. Any questions on that? Any questions? Okay. And the way I program this, the x-axis is actually below the screen. So I put in the numbers, but not the line, because the line's way below it, because nobody's even close to, you know, 0 years old. Okay, any questions on the scatter plot? Okay, so then there's a whole lot of other things. Then there is the equation of the regression line. So this is y is equal to about 25 plus 0.28x-ish. Okay, and I want to remind you that when you read a line like this, the equation of a line, the number in front of the x is the slope, and the number without the x is the y-intercept. So again, that's a review from beginning algebra, but it happened once in your life, maybe more than once, but it is important. Okay, stop me if you have any questions, by the way. So the next thing we have here is R. R is called the correlation. So R is a correlation. And as we saw that I showed you a little bit ago, is that R is always a number between -1 and 1. Okay, in this case, it's 0.96. If R is close to 1, that means you have a strong positive correlation between the two numbers. Okay, which shouldn't be too surprising in this case. So that says that as we look at people who have had more quarters in college, they tend to be older. Again, I'm sure none of you are shocked about that. Okay, that does not mean that it's always true for every single person, but it is true in kind of as a prediction, kind of in general. Okay, so yeah, it turns out if R is equal to 1, then that means the points all lie on a line of, and that line has positive slope. So and that can happen, but it pretty much only happens if there's some kind of forced relationship. So for example, if I asked you the two questions, the first one is, how many inches are you in height? And the second question was, how many centimeters in height are you? Okay, that, if you do your math right, by the way, in terms of your own height, that will have an R equal 1, because there is a direct linear relationship with a positive slope that relates height in inches and height in centimeters. Does that make sense? Okay, so pretty much that's the only time you're going to see a perfect R equals 1 is when there is a mathematical relationship between the two variables. Does that make sense? Okay, on the other hand, you'll often get like an R equals 0.96, because then we don't have a direct mathematical relationship between how many quarters you've been in college and how old you are, but it helps you know, if someone tells you how long they've been in college, that gives you an idea or a good prediction of how many quarters, of how old they are. Does that make sense? Okay. Any questions so far? Okay, if R is negative, it's the same idea, except then you have a negatively sloped line. Okay, and that might be something like maybe how many hours people watch TV and how many hours people go outside and play. Okay, my guess is that people who spend a whole lot of time sitting around watching TV probably are more likely to spend less time outside playing. So as one goes up, the other tends to go down. Okay, it's not a perfect predictor, but you're going to have this negative relationship between the two. If R is 0, that means there's neither a positive nor a negative relationship. So a good example that I like to give for an R equals 0 because all of you have seen this. And that is, if you go out at night and you look up, what do you see? Although it may not be true in San Francisco, in Tahoe, you see stars. Okay, is there like a linear relationship in the stars? They're just kind of all over the place, aren't they? Okay, so if you look at kind of the stars looking up in the sky, and you looked at that as a scatter plot, kind of in any XY axis you want, then you're typically going to have an R pretty close to 0. Okay, it's not like the stars are all lined up. They're just all over the place. Does that make sense? Okay. Another time you're going to see an R is equals 0 is if they follow a parabola on both sides. So there's a perfect relationship, but they go down and then go up. So there isn't a positive and there isn't a negative relationship. Okay, that comes less often in applications than more of the no relationship at all kind of thing. Another example might be things like the temperature in Tahoe and the score of the Australian football game on that day in Australia high school. Okay, if you know how hot it is in temperature, you probably have no idea what the home team's going to score in Australia because they have nothing to do with each other. So if two things have nothing to do with each other, you're usually going to have R equals 0. Any questions on the idea of R? Okay, then comes R squared. Okay, R squared is, it might be obvious, but you take R and you square it. But it's actually more than that. One thing is that R squared can never be negative. Hopefully you all now know that from math, right? If you square a number, you don't get a negative number. Okay, so it's going to be between 0 and 1. But R squared actually has a kind of a specific meaning that helps us out to understand. And here R squared is, I like to use 2 decimal places because I like to think of it as a percent. And in this case, it's 92%. Any questions on that idea? First thing? Okay, now here's what it's a percent of. So if we look at the scatter plot and we look at these points, and if you only look at the Y variable, in this case, the ages, then the ages of people have a pretty big range. Do you see that? They go from 22 to 55, right? And they're kind of all over the place. Okay, and this is just sample size of 5, which is tiny. Okay, so if you had a bigger sample size, it's more meaningful, but they're all over the place. On the other hand, if we don't ignore the X variable and we look at, say, only the young people, I'm sorry, not only young people, only the people who've only been to college not that many quarters, then you'll notice that the variation, the range or the standard deviation is even better, is smaller if we focus only on this group. Okay, and when you have a sample size of 5, nothing's very meaningful, but if you had a large sample size and you had an R squared of 92%, then what you can say is that on average, if you know the value of the X coordinate, then the standard deviation will decrease by 92% on average. And that's a big drop in standard deviation. Whereas if you just look at all the data without paying attention to the X variable, if you just look at the Y values without even looking at the X, then that's going to have a big variation. But if you only focus on the Y values that are all have the same X value or close to the same X value, then on average, that variation is going to be decreased by a factor of 92%, which is a big decrease. Okay, so it's a Y variable standard deviation that gets decreased if you only focus on the values of Y that are near the same X. Okay, which makes some sense. So if you look at people who are just starting out in school, then you're going to say, well, you would expect that the age brackets are going to be pretty young, right? You're not going to have that many young, old people. They're all going to be a lot of 18-year-olds and 19-year-olds. Does that make sense? Okay. Does it always decrease? No, because if R is 0, R squared is also 0, right? So if the two variables have nothing to do with each other, then knowing one isn't going to tell you anything about the other and decreasing. Yeah, explains is another word. But explains is just kind of vague. That's why I like variation decreases. Because what does explain really mean? Okay, but what you can say is that kind of 92% of the variation will decrease by that. But then there's other factors that might be involved. And that will attribute to the rest of the decrease in the variation. Does that make sense? Okay, so that's the idea of R squared. Does it ever increase? No, not on average. Yeah, R squared, and that's because then R squared would have to be bigger than 1. So you won't have an average increase. Okay, so then there is a hypothesis test. So I'm kind of going through all the different things in regression analysis for this example. This is a fun little example, worthless because there's only 5, data set of 5, by the way. But we can do a hypothesis test. In our class, you're always going to click this first one. Okay, for most things, unless the only time you're going to go less than or greater than is if you want to have a hypothesis that there's a positive correlation between the variables, then it's a greater than. If you want to have a hypothesis that's a negative correlation, then it's the third, then it's the greater than. I mean, sorry, if it's positive, it's greater than. If it's negative, it's less than. Okay. If you just want to find out if they're correlated, and a lot of times you want to find out if they're correlated because if they're not correlated, then don't even bother using this data in terms of trying to get any kind of relationship. But if you just want to find out, is this useful, then you're going to go for the not equal to. So we go for the not equal to. And again, I can't get into the details because the math is too hard, but the test statistic mathematically turns out to be also a t-distribution. Remember we had that in chapters 9 and 10? So it turns out that the math gives you the same thing. You know, I kind of throw that under the carpet, but you can trust me on that. But p-value is something you do understand, I hope, and it's the same idea. So we have a p-value of 0.009. What does that tell us? Yeah, there's statistically significant evidence to conclude that there's a correlation between the number of quarters students have been on campus or in college and their age. Okay, and it turns out the p-value is the same no matter which one you choose for the dependent variable. So if we switch x and y, you'll still get 0.009. Yeah, I told you this is worthless because we have a sample size of 5. Okay, so first thing we did convenience sampling, that's a problem. Second thing, we had a sample size of 5, that's even a bigger problem. And when you have a sample size of 5, that means you have to assume that you have a normal distribution for every value of x. And I have no idea if the age for those who have been in a certain number of quarters of college is normally distributed. I doubt it is. So there's all kinds of bad assumptions you have to make when you have a small sample size. So let's just, like I said, we're doing it because that's all we've got here. So now let's do something more realistic. Okay. And those of you who live in Tahoe probably know, what's the most important data that's collected in Tahoe? Where it's not, and by the way, you cannot collect it anywhere else other than Tahoe. That's a hint. Yeah, Lake Tahoe water quality. Okay, Lake Tahoe water quality. And in particular, we're going to measure, and this is what UC Davis, by the way, is in charge of the research that's done for water quality. And they do a lot of indicators, but their main indicator for water quality is clarity. Okay, is clarity. So I'm going to go back. And this comes from UC Davis. Okay, and they use what's called a Sikidis, which is basically just a little white plate. And they take that white plate and they have it tied to a big rope and they drop it down until they can't see it anymore. And they measure how far they dropped it, and that is the clarity. That's how they do it. It's very simple. And they do it every year. And you want to hear something great? This made me smile, like more than anything makes me smile when it's related to us. And I talked to the researcher at UC Davis. They happen to be doing some kind of environmental something. It might have been environment day. And so I got to talk to him all about how he did it, how their group did it. And I asked him, well, when you do it, do you just take one, you just do it once and that's it? And he said, no, we do it multiple times. I asked him, how many times a year do you do it? I told you it made me smile. Any guess? This is what he told me. Now, 12 would not make me smile. That'd make you frown. All right, I think I'll tell you, 31. I was just smiling so much because 31 over 30 is in our class, and a lot of other classes too. Over 30 means you don't have to make an assumption about a normal distribution. And they took the average of 30 samples, and from the central limit theorem, if you take 31 samples, if you take an average of 31 samples, then by the central limit theorem, you have an approximately normal distribution, and then you don't have to worry about that. Okay. And it's not quite 100% random because you can't do it on a sunny day, if I remember right, because there's reflection. So you can't actually see anything. So they had to do it on cloudy days. But they did it throughout the year. And that's what they did. And this is the data. And I was able to go to their website. Okay. In fact, I went today to the website. And I'm going to talk to you about another story. Also made me smile. And this came from a student of mine. This was a very long time ago. Okay. This was in the end of this last century. I've been teaching a very long time, by the way. And she got to experience this firsthand. The most important person in the entire country came to Tahoe. You don't know who the most important person in the country was then? Yeah, Bill Clinton. And Bill Clinton came to Tahoe for the Environmental Forum. Isn't that cool? And the research group showed him this. And one of the great things about Bill Clinton, I don't know if you know, but he took statistics. And he understood statistics, which is good. I think all presidents should understand statistics. And he was shown this scatter plot. And we have the scatter plot. And this is a scatter plot. They've made it pretty. Okay. And it's a little tricky because I'm going to ask you a question and you might get it wrong. If you kind of visualize the best fitting line to this scatter plot, are we going to have a positive correlation or a negative correlation? Okay. All right. Yeah, this is a trick question. It's a trick question, but this is the way UC Davis shows it, so I have to show it this way. And that is the y-axis is upside down. So notice as the years have increased, we have a tendency of the meters of clarity to go down. Okay, and that happened, again, this is what they showed to the President of the United States. Okay, and actually some senators and there were a whole group of important people. Okay, and she was there because it was at a restaurant and she was their server. Isn't that cool? I wish I was working in a restaurant that day. So this has really happened. And so what we can do now is we can take this data now that we see the scatter plot, and we can visualize that there definitely seems to be a relationship between year and clarity. And as the year has gone up, we definitely look like the clarity's gone down. You notice that? So what I can do, and by the way, in the year 2000, this was a lot harder than it is now because these calculators didn't exist, is I can start over. And by the way, if I hit refresh, that clears it up. So I can start over again. Makes it a lot easier. And that's true on any of these calculators. Hit refresh if you want to clear everything. And I can copy and paste these numbers in. And I made sure that I prepared ahead of time so I didn't have to type all these numbers over again. This took a long time today. I did this today. And I typed all these numbers out from the website from UC Davis, this site. And I pop them in. And we definitely want to do the hypothesis where rho equals 0 and rho not equals 0. And I'm going to click plot points. Okay. And now, by the way, the scale is more of what you're used to mathematically. So it goes up on Y with depths of clarity. They wanted to show the boat, and so it went down for deeper. You know, that would be more clarity if you can see farther down. But now we're just looking math. And here's the scatter plot. And let's look at R and R squared. First thing, what do you notice about R in this case? R is negative 0.91. Yeah, now it's close to -1. What does that tell us if R is close to -1? Yeah, we got a strong negative relationship. Okay. We got a strong negative relationship. That means that year is a good predictor. Another thing we can say is that definitely things are getting worse. By the way, not much clarity is bad in Tahoe. So if you're not from Tahoe, I will tell you, we want to be able to see really deep. We want clarity. Okay. So that's a big deal, is that clarity has been going down. Okay, we also have the slope is negative 0.28, and the y-intercept is 48.27. We have a test statistic of -12 point something. Is the p-value 2.56 about? How come? Yeah, why is it not about -0.56? Yeah, that E -13. So I want to focus on that because a lot of people don't look far enough to the right. What is that E? Yeah, that E -13 means that there are 12 zeros before the 2. We got to move that decimal over 13 places to the left. So this is a very, very, very tiny number. So there is no question in anybody's mind that there's a correlation between year and depth of clarity. Okay, this is about as reject the null hypothesis as you'll ever get, because that's a tiny, tiny, tiny p-value. Any questions on that? Okay, so let's interpret some of these things. Let's start with a slope of -0.28. So I can go back so I can start typing things out. So let's go to -0.28. And I know this might look a little weird. I'm going to write 0.28 because this shows better on the screen. I'm going to put over 1. And it's like, why would you do that? But there's a reason. When you think of slope, what words do you think of? What words were you taught? Rise over run. So it helps to have an over one so that we can understand this a little better. Does that make sense? So then let me write this as rise over run. So the rise, that's a change in the y value, right? The y value is the depth of clarity. Change in the depth of clarity. Run, that's the x value change, and that's a change in the year. Any questions so far? All right, so in this case, here's what we can say. Well, the rise is negative 0.28, and the units are meters, by the way, because it says so. And the run is 1, and the units here are years. So here's how we can interpret the slope. Is for every 1 year that passes by, the depth of clarity has tended to go down by 0.28 meters. Is that okay? Do you think Clinton said, oh, no problem? Okay. Yeah, so the question is on average, you can say on average, the word tended to, that gives you the average. So I'll throw an average if you want to put that in, but you have to have the word tended to say average if you want to say depth of clarity on average. Has tended to go down. It turns out those mean the same thing because the word tended has the average in there. That's all part of tendency. But it can't hurt to like doubly say it. Okay, so do you think that's okay? Environmentally? Let's find out. Let's do a prediction. So based on this, actually one more thing before I do the prediction, let's interpret the y-intercept or state why it isn't very useful. So the y-intercept, just remember, that was about 48. Okay, so what's the x coordinate of the y-intercept? Always, in any situation, 0. So note the x coordinate of the y-intercept is always 0 by definition. Any questions on that? Okay, so is this very useful? Because the x coordinate in this case corresponds to the year. Do you really think that we should be using this data to predict the year 0? Yeah, probably not. Okay, probably not. Okay, so we really don't want to use this data to predict the year 0 because the data that was taken 0, remember that this 65, that This 65 is not really 65. That's 1965. Does that make sense? The year 0 is ridiculous. Okay. It doesn't even make any sense. Does that make sense? And our y-intercept, again, was 48. And these are meters. You're not going to be able to see 48 meters. I mean, that's just silly. So in this case, the y-intercept is not very useful. Since the year 0 is way, way far from any of the data points. Okay, data can only predict so far away. Any questions on that? Okay, so I want to let you know there's a few reasons why the y-intercept won't be useful. One is if it's way too far away from all the data points. Okay, like not even an order of magnitude compared to what the data points spread are. Another is sometimes it doesn't make any sense. So for example, if we did something with depth of clarity and found out the y-intercept was -30, why does that make no sense? If we did the same experiment, but we found -30 for the y-intercept. Yeah, you can't have a clarity above the surface of the water, right? That doesn't make any sense. So sometimes the y-intercept doesn't make any sense. Sometimes because the value doesn't make sense. Sometimes the number 0 doesn't make any sense. Okay. So for example, if we looked at age versus, say, age versus how about how fast you drive. Why does the y-intercept make no sense in that case? So age versus how fast. Yeah, newborns don't drive. When you give birth to a baby, that baby does not jump in front of the car and start driving. Okay, so it makes no sense to have a y-intercept. Okay, the number's there, but it doesn't have any meaning. Does that make sense? So that's just a note. Sometimes it does have a meaning and sometimes it doesn't. On the other hand, let's say we looked at the amount of studying students do in getting ready for their, let's say, next exam versus their percent score on the exam. Why might the y-intercept have meaning in that case? Let's say the y-intercept was 42. Yeah, because there are students, I wish there weren't, but there are students that don't study at all for their exam. So then you would say that the best prediction for a student who doesn't study at all for their exam is 42% on their final. Any questions on that idea? And that would be useful. Okay, in this case, it's not. Okay, but we're going to continue on. Let's do another question. What is the best prediction for the lake clarity today? How do we come up with that? How do we make a prediction, the best prediction for the lake clarity today? Any thoughts? I don't see y'all jumping in. Might help to see this, especially this. past research, but in particular, what did I just highlight? Okay, actually don't have to solve for X. We're not solving for X, we're plugging in X. So today, by the way, 99 was 1999. So the year 2000 was 100. So today would be 122. Any questions on that? So today would be 122 because that's the, we started at zero. Zero in this case was the year 1900, actually, the way these X's are drawn. So we're going to go 122 and plug in. So I'm going to do it this way. I'm going to copy. I'm going to go to scientific calculator, paste it in, and I'm going to take my X, make it times 122. And what we get is a lake clarity of 14 meters. All right, is that okay? Okay, so again, here we are. That's like what we would expect is that today the lake clarity would be like here, like right there. Do you think our political people were okay with that? As that is a prediction? Yeah, no. So let me tell you what happened. This is why I love it so much, because this was actually used. So what happened is President Clinton and the members of Congress who were there at this forum, this meeting, went back to Congress. And they actually, and I don't know if any of you were involved in the funding, but they passed a bill in Congress to protect Lake Tahoe's clarity. And they put in many, many, many millions of dollars. I think $100 million to protect us. And that went into all of this research, all of this BMP, if you've heard of BMP, best management practices, and a lot of work on making sure that we do everything we can to make this not happen. Does that make sense? So now do you want to see what has happened since that happened, since the bill? Okay, so let's take a look. So this is the most recent, okay, data that we have. And notice what's happened since the bill, since 2000. What do you notice about lake clarity after the year 2000? What do you see with the scatter cloud? Yeah, all of a sudden it actually didn't get better, but it didn't get worse. Okay, it didn't get better, it didn't get worse. It's kind of up and down. So let me talk about this right here, and that's the R squared. This was the R squared from the previous time. That's about 0.84. Let's write this down. So let's interpret R squared. Where was I? Over here. So R squared, let me write it this way because often you'll see this. R squared was equal to 0.84. So what we can say is that there has been a lot of variation in lake clarity over the years. But if we just focus on years that are all close to each other, then the average variation in lake clarity is 84% smaller. So we have a reduction in variation by 84% on average if you use the year to predict Y. Okay. One more thing that I want to do with this particular example is our hypothesis test. We already had, by the way, H naught, rho equals 0, HA, or H1, you choose whether you want to use it. What is close to each other? So that's actually a little too complicated to talk about. So we're just going to do it by feel. Okay. So it's how good your prediction is, kind of. So I'm gonna hold off on that one because it's not elementary stats, it's advanced stats. And the definition, it's too much. It needs lots of calculus. Okay, but we know what R squared is. So for H naught and HA, HA is rho is not equal to 0. We got a mini p value. So when there's a mini p value, that means there is strong, very strong statistically significant evidence. So let's write that out. There is very strong statistically significant evidence to conclude that there is a correlation between year and lake clarity. Let me make that bigger for you. Any questions at all on the hypothesis test? All right. Let's look at the last 20 years of data. So from 2000 to 2020 is what I was able to get from the UC Davis website. So to do that, I'm going to grab the data from 0 to 20. We'll do years after 2000. It'll be easier. I'm going to copy that. Let's refresh this guy. I'm going to paste. And then this took a long time. I typed in all the numbers. And copy those numbers, separated by commas. I'm going to paste. And then I'm going to plot points. Now, what do you notice? Just by looking at it, looking at the scatter plot. Does it look just like the first 20 years we looked at or so, first bunch of years? No, not at all. In fact, if I told you these were stars in the sky, would you believe me that that could be true? Yeah, it looks like the night sky, doesn't it? Okay, so now let's see what we get. So we get y equals 22.2338 plus negative 0.0948x. But now we have r is negative 0.41, much closer to 0 than what we had before. Okay, and r squared is only 17%, which is actually a very small percent compared to 84% is what we had last time, actually, for the beginning years. Okay, the p-value is bigger than 0.05. Not that much bigger, but it's bigger than 0.05. So we fail to reject the null hypothesis. And if we do not have statistically significant evidence to show that there's a correlation, then you shouldn't even try to interpret the slope and the y-intercept because they're not very helpful. Okay, we can interpret r squared. You can always do that, but notice that it's saying that you only get a 17 on average, a 17% drop in the variation by knowing the year. Okay, most of the rest of the variation is due to other causes. This isn't a math question, but this is another question. See if anyone knows. What's the main cause now of the variational lake clarity? Anyone know? And I know because I've actually researched all this stuff because I care. Good. Yeah, weather. Yeah. So the main cause is weather. Okay. If you have a big storm year, then you're gonna have a lot of water runoff when the snow melts. And then because of that lot of runoff, you're gonna have less clarity. Whereas if not much runoff, you're gonna have more clarity because there's less stuff going into the lake. Okay. It's still less in the 70s, but it's not substantially less than it was 20 years ago. And that's since they passed that bill. So what they did is they passed the bill, and what they did is they were able to stop the decrease in lake clarity. They were not able to get it back to what it used to be, but they were able to stop the decrease. Okay, any questions? And I love this week because this is my favorite statistics example, because it shows how statistics made a positive difference to something that I care about a lot, which is Lake Tahoe. And if you're not from Lake Tahoe, sorry about that, but I care about Lake Tahoe. Okay, and wherever you're from, I'm sure they do environmental stuff, although there's some places that don't do a good job of it. Okay, so this is why you need to listen to statisticians, because statisticians will look at things and show you what's going on, and you'll be able to see whether you have statistically significant results or not. And if you do, then you should pay attention and do something about it. If it's statistically significant results that show something bad is going on, then you want to do what you can. Okay, you're going to be able to see the bottom of, not from the deepest point. Look at these meters, by the way. I don't know if you guys realize, but we're talking, and if you want to do feet, you can. So it's never been over 110 feet, even since 68. Okay. Do you know how many feet Tahoe is? Yeah, lots. In fact, I don't know if you know, the bottom of Tahoe is lower than Carson City. Yeah, it's like 1,200 feet. Yeah, so forget 1,200, but that just wouldn't happen in terms of nature. That's never going to happen. Okay, but 100 feet is a lot of clarity. You can see them way deep. So again, you got to see what's reasonable. Any questions at all on this whole idea of regression analysis? Okay, since I'm here, although I still have more to say, but I figure I'll pop it in. And that is, a secret word for today is predicted, because it's about what we're about to talk about. So what we can do is we can use, if you have a low p-value, then you can use the regression line to make a prediction about what's going to happen in the future, or what's going to happen with that age person, or what's going to happen, given the value of X. So that's predicted. Okay, so anyway, predicted is the word for the week. So just a note, here's what you cannot do. You cannot use the words cause. So here's warning. Never use cause. But there's by the way, there's a longer word with the word cause in it. Y'all know what it is? Yeah, because. And a lot of people don't even realize it. They don't even think that it's because has the word cause in it for a reason. It's caused by. Okay, so beware of those words with just regression analysis. Okay, does that mean that the X cannot cause the Y? No, it doesn't mean that either. It just means that if you only have regression analysis and that's all you have, that's not enough. So an example, let me give you an example. Let's suppose, and this was done, a study was done of smoking. They asked people how long they smoked. Sorry, how many cigarettes they smoked. And then they waited until they died. They wanted to see how old they lived. And they came up, let's suppose they came up with a correlation of say 0.9 with a really low p-value. So based on the correlation of 0.9, okay, r squared of 0.9. Let's take out an r squared of 0.9 and a p-value of 0.0001. Based on that, can you say that smoking causes premature death? Okay, the answer is no. What you need is you need medical people to team up with the statisticians. Okay, so this is not mathematicians solving the world problems. This is a team of scientists and mathematicians. And what usually happens is the statisticians see this high correlation. So then they go to the doctors and the medical researchers and say, we found a high correlation. Can you take a look and see if there's any cause? So then they go and they do autopsies and they find out and they look at the lungs and they realize that there are real bad lung problems with those that smoke. And they realize that the cigarettes were causing lung problems. So the statistics backs up what the medical doctors and researchers were able to see. And it's a collaboration between the scientists and the statisticians that can come together, and then you get a cause. Okay, and if you don't have both, you're not going to be able to publish that you have a cause in a peer-reviewed journal. And you're not going to convince the FDA or whatever organization you might need to show cause. Does that make sense? Okay, so, and there's examples where it may feel like a cause and it may not be a cause. Okay, and we don't know, and it's really hard to know. So I watched a psychology lecture, okay? And a good example of spurious coefficient correlate. Okay, so here's one. All right, let's look at people and let's count the number of gray hairs they have. And let's look at their age. Okay, I have some gray hairs, by the way. I don't know if you can see, but I have some. I'm not all gray, but I do have some gray. Okay, and if you look at the number of gray hairs and you look at the age, do you think there's going to be a correlation between the number of gray hairs and the age? So do you think old people are going to tend, do you think people with more gray hair are going to tend to be older? Doesn't mean 100% older. Yeah, there's definitely a correlation. Does that mean that if I go to one of you young people and I dye your hair gray, I'm going to cause you to be old, a whole lot older? What do you think? Yeah, definitely not. Okay, you'll be a few minutes older because it took a few minutes to do it. But making your hair gray does not cause you to be older. Okay, and in fact, in this case, it causes backwards. Okay, age does cause gray hair. Okay, and again, that's a combination of statisticians and medical researchers. Okay, actually, I don't know medical that makes your hair gray, but I know there is some, because I'm not a doctor, I'm a statistician, but I can actually back up this medical researchers' ideas with a small p-value. Do you see that? So that would be an example where it's a one-way cause, not a two-way cause. Do you see that? Okay, yeah, it could be, and by the way, just because you have high correlation does not mean that's the only thing that is contributing. Sometimes there's other things that contribute. Any questions on that idea? Okay, then there's sometimes you'll get a correlation and it doesn't have a cause in either way. It could be that something else is causing both. Any thoughts of an example where something causes both? Because there's lots of them. Where one thing causes both, but they don't cause each other. Okay, so econ ice cream and crime, when it's the weather that affects them both. Okay, yeah, that's definitely one. Is that hotter weather? So it turns out if people are eating more ice cream, there tends to be less crime. That is not because ice cream makes more criminals. Okay, and by the way, more criminals don't make people eat more ice cream. Does that make sense? So in this case, what's happening is that high temperature actually causes both. If the temperature is higher, hopefully you all know that people are going to want more ice cream. And what you don't know, and I have learned this, I was a sociology minor. I actually learned it in my sociology class, not my econ class. I learned in my sociology class that if you have a higher temperature, there tends to be more crime. Okay. So that would be an example of two things that are caused by something else that don't cause each other. But there is a correlation, it's a negative correlation, between the amount of ice cream consumed and the amount of crime that happens in town. Any questions on that? So that's a great example. So beware of cause. Sometimes you have cause, sometimes you don't, but you can never state cause just based on the regression line. You can only state predictions. You can state tendencies those are the words you tend to use in regression analysis. You do not use the word cause, you do not use the word because. Another word that you should be careful about is will. So something like, I don't know, if you found out there was a correlation between the amount of money people have and the amount of time they spend away from their town, then you cannot say that giving people more money will make them spend more time outside of their town. You can't, be careful about the word will, because will is the same as a cause. Okay. Yeah, there's a lot of great examples of funny examples with correlation and causation that are just wrong. Okay, so that's about it. It's about 1:20, which is kind of around my goal. So usually what I want the webinar to be about an hour and 20 minutes. I don't want to like bore you to death by making it 2 or 3 hours, but an hour is almost never long enough. I want to let you know that next week we will have our webinar. Do you remember what day? Yeah, that's Monday, and that's actually our last webinar. It's the last webinar of the entire class. Okay. I don't put one during finals week because some of you have already taken the last test and done all the work, and there's no reason to have a webinar after you're finished with the class. So next week will be the last webinar, and it won't be that intense, actually. That's good news. ANOVA is not one of the harder things. And it's not like this is the first time, and maybe you can tell me, is it working? The fact that we don't have like 2 main exams. We used to just have 2 exams, midterm and a final, and that was it. And that was your grade mostly. And now we have every other week we have an exam, and that's a big part of the grade. But it's each exam is not as like killer because I'm trying this is new. I've never tried it before, and I never talked to anyone else who's tried this particular thing in a stats class. Okay, so I'm going to stop the share and stop the recording.